Now in the past section we talked about what a permutation was. So a permutation was a ordered arrangement of a given set of objects, and then when you're arranging the objects they can't be repeated. In a combination, the order doesn't matter. So a combination will be any unordered arrangement of a given set of objects, and again their repetition is not allowed. Repetition is actually not allowed in both cases, so the key thing in this one is this is unordered. So suppose Al, Betty, Carl, and Dan are in a class and the teacher needs two of them to go to the board to put up a homework problem. Now order won't be important here, so the idea is once you've been chosen to the board, you've been chosen, right? It's not going to matter to you whether or not you got called up first or called up second. It just mattered that you had to be the one to go up there. Okay, so the question is, how many ways is there to send the students to the board? So for the first student to be picked, it could be Al, Betty, Carl, or Dan. And then we don't want to pick the same student again, so at this point in time I'm going to go ahead and fill out my tree, kind of how we've been doing the tree diagrams, and then we're going to talk about how the order doesn't matter. So if I pick B first, we would normally branch out for A, C, and D. If I picked C first, I would normally branch out for A, B, and D. So this is the tree that we made when we did our permutation case. Alright, so at this point in time, if I were to start recording my sample space, you could have AB, AC, AD. You could have BA, BC, and BD. You could have CA, CB, and CD. Or you could have DA, DB, or DC. Now this one though, we are counting Al and Betty going to the board. This is being counted differently than Betty and then Al. But for a combination, it doesn't matter that those two went to the board. So we don't want to count these two differently. So we're going to throw this one out as being a different arrangement. So order is not going to matter. It just matters that I have those two students. So we're going to have this one that we're going to keep. Now I'll have Al and Carl, so I want to throw out the one that has Carl and Al because we don't want to keep that one differently. Al and Dan, so we're going to throw out Dan and Al. And I'm just going to keep going through here. So if I already have B and C, I don't want C and then B. If I want to keep B and D, I don't want to keep D and then B, where it's the same thing. And then CD will be counted the same as DC. So then at this point in time, how many do I have left? 1, 2, 3, 4, 5, I have 6 left. So if you just try to throw either the counting principle at this or permutations, you would have gotten that there's 12 ordered arrangements. But order is not going to matter in this particular case. So for each one of these, you could rearrange it 2 factorial or 2 times 1 or 2 different ways. So we had to divide out how many ways it could be repeated, and then we've got 6 unordered arrangements. Okay, so the key thing when you're doing a combination is you have to throw out the repetitions. So that's what's going to be accounted for us in our formula. So for our combination formula, you've got your big C in the middle to represent a combination, an unordered set. N is still going to be the total number of objects. R is still going to be how many you want for your set. So to determine the combination, then the formula is going to be n factorial over r factorial times n minus r factorial. Now, parts of this should look very similar to the permutation formula, and for good reason. We kind of start with this permutation idea of taking the ordered arrangements, and then we're going to divide out or reduce it by the number of ways that the set can be repeated. Okay, so this is the new factor right here, this r factorial. That effectively gets rid of the duplicates for us. Now, without getting too involved into it, and you won't need to record this in your notes, but let's say, for instance, you would have these 4 people, but you wanted to pick 3 of them, either to go to the board or maybe to form a group for group projects and things like that. So you wanted to find out how many ways to arrange them. Okay, so over here I have a tree diagram that I've already built. So for this one, you've got your 4 people at the beginning, and then depending on who you picked here, it dropped down to 3 people in the next branches, and then 2 people for the last branches. So the tree diagrams we're kind of used to drawing at this point. So then down here I've listed the sample space. So 4 times 3 times 2 would give you 24 different outcomes, or 24 permutations of these letters if you were to pick 3 of them. So for each one of these arrangements of 3 letters, they occur in 3 times 2 times 1 or 6 ways. So for instance, ABC, and I already have them out here marked in red. So you've got ACB, BAC, BCA, CAB, and CBA. If you're doing a combination, all of those are going to be considered the same. So at this point in time, what we're going to do then is we're going to start removing out the duplicates. Alright, so we're going to pull out all the ones that are like this one. Okay, so all those red guys are gone. Now let's go out and pull out all of them that are like A, B, and D. So that'll be all the green ones. So they're gone. Let's start pulling out all the ones that look like A, C, and D. So that'll be all the other blue ones. Those guys are gone. And then finally, any of them that involve B, C, and D in some sort of order. So then those guys are gone. All right, so then what we're finding then is that there were 24 permutations. Because we're having arrangements of 3 of them, that'll be 3 times 2 times 1, or 6 ways to keep rearranging each one of them. So if we take the number of ordered arrangements and divide by 6, that leaves us with the 4 possible combinations. If we have 4 items total, and we want to arrange 3 of them in an unordered set. So then ultimately how this connects to our formula is that the n factorial over n minus r factorial, that was your permutations, and you're going to divide out the number of ways to permute each set. And the number of ways to permute each set, r is the number of items you want in your set, so there's r factorial ways of rearranging them. So dividing by a number is the same thing as multiplying by that number's reciprocal, so that's where this next step comes from. And then if we just multiply across the top and multiply across the bottom, there's the combination formula that we are going to be now using.